Chapter 7 is on first-order circuits, and a first-order circuit is characterized by a first-order differential equation. Now, you may or may not have had differential equations yet. If you haven't, it's okay. We'll go over enough so you can understand what's going on. If you have had differential equations, then this should be nice for you because you'll actually see that they are useful. Don't tell the math teachers I said that. Okay, so for our purposes here, a first-order circuit is going to mean that we either have a capacitor or an inductor, not both. Chapter 8 will do second-order circuits, and in that chapter we will have an inductor and a capacitor at the same time. So we're just going to deal with one at a time. So 7.2 is on the SourceFreeRC circuit. So we have a resistor, and we have a capacitor, and we have some switch. So we're assuming this switch has been closed, and then it opens at some time 0. And we want to know what happens when it opens. Well, we know that when the switch is closed, this capacitor is going to charge. And when the switch opens, it's going to discharge. So we want to find the equation to show the rate of the discharge. Okay, so let's define a couple more things here. I'm going to define an IC and an IR. And yes, they're both leaving. So I know IC plus IR are going to be equal to 0. Again, we're looking at after this switch is open. So after this is open, this is no longer connected. IC, the current through a capacitor, is C dV dt. And the current through an inductor, using Ohm's law, is V over R. So I have this equation. And if I rearrange this, I get what's called a first-order differential equation. So this is a first-order differential equation. Whoop. All right, so we want to solve that. So we're going to rearrange a little bit. Going to write dV over V equals minus 1 over RC dt. So again, I haven't done anything but rearrange. Take the integral of both sides. So integrate, integrate. And I want to integrate from some initial voltage to some final voltage. And from 0 to time t. Got a tickle in my throat from the board cleaner. So you get ln of V is equal to, I didn't mean to write that. Well, that's okay. I guess we can do that. We just need to evaluate it from V0 to V. I'll do an extra step here. And for this, we get minus 1 over RC from 0 to t. So I have ln of V minus ln of V0, V naught, equal minus 1 over RC t. So I can write ln V over V0 equal minus 1 over RC t. Take both of those to the power of e and rearrange. And I get V of t equals V0 e to the minus t over RC. And this is a very important equation here. And I should also write this is for t greater than or equal to 0, right? Because when t is less than 0, that switch is closed. When t is less than 0, I can actually solve that very simply. If t is less than 0, then my capacitor looks like an open. Everything's in parallel. So my V of 0 is V naught. So this is saying at time 0, right when the switch opens, my voltage is equal to V naught. Then it's going to decay according to this equation. So if I want to know some time, what the voltage will be at some time, I can plug it into T. I know RC, I know my initial value, and I can find the equation for how, or find the particular value for what it will be. We define tau as RC. We call this the time constant. Again, you've seen that in physics class if you've had physics. I hope you have. And this will decay at about 5 tau, so that's just a rough estimate. But approximately 5 tau is when our capacitor will be discharged. So a few key points in how to solve these problems. The first one, you need to find your initial voltage. So the switch is closed. Assume the switch has been closed for a long time so that your capacitor looks like an open. Find your initial voltage. Second step is to find tau. Tau is simply equal to RC, but you may have a network of resistors that you need to put in series and parallel or whatever. And make sure you're only looking at resistors that'll be present after the switch opens. If you have a resistor over here, that doesn't count for tau, right? Because tau is after the switch opens. So it's everything beyond the switch that's connected to our capacitor. And then 3 is just simply plugging these values in to this equation, and you'll have your answer. And of course, once we have our V of t, then it's easy to find IR, IC, or IR of t. We're just using Ohm's law. So it's going to be V of t over R. And for IC, well, we know that equation, right? I equals C dV dt. So it's C dV dt. Take the derivative of our V of t, and you get minus 1 over R, V naught, e to the minus t over tau. I'll be posting an equation sheet online. It's going to have a lot more information than you need at this point, so just use it, use the first part of it, and then you're going to learn about the second part later. But this equation is on there, and I want you to get used to using that equation sheet because that's what you'll get to use on your final exam that you have to take on campus. So get used to the equation sheet now. We'll work some example problems in the next video.